Panda obtained the PhD degree in the electrical engineering from National Institute of Technology, Meghalaya, from July 2013
Madam,
June
your voice is uninterrupted.
2017 assistant professor. Sir,
No, no, you please carry on. Please carry on.
sir, good morning, sir. I hope I'm audible.
Yes, yes, you're audible.
Please, you're audible.
Uh, uh, so participants, kindly mute yourself. Thank you. So, before proceeding, I would like to introduce our next speaker. So, Dr. Kaibalya Prasad Panda obtained the PhD degree in electrical engineering from National Institute of Technology, Meghalaya, Shillong, India in 2021. From July 2013 to June 2017, he was an assistant professor with the Department of EEE, C.V. Raman College of Engineering, Bhubaneswar, India. After his PhD, he served as ad hoc faculty in NIT Andhra Pradesh from October 2021 to June 2022. Currently, he is working as an assistant professor with the Department of Electrical Engineering, School of Technology, Pandit Deendayal in Energy University, Gandhinagar, Gujarat, India, since September 2022. His research interests include reduced switch, multilevel inverter design, new power converters, power quality control, and photovoltaic system applications. He was a visiting scholar with the University of Warwick, UK during January to March 2019, funded through the joint UK India Clean Energy 2 months exchange program scheme. He was recipient of Professor Subhasis Nandi Student Travel Awards for Power Electronics, Drives and Energy Systems, PEDES 2018 Conference and IS Travel Grant for Power Electronics, Smart Grid and Renewable Energy conference. He has received the Institute Best Research Award during his PhD and Best Paper Award for one of his papers presented in ICEPE 2020 conference. He has authored or co-authored of over 10 IEEE transactions and reputed journals or conferences and also filed 2 patents. Consecutively in 2021 and 2022, he has been listed in world's top 2% of researchers under the energy category as per the Stanford University list. He is a regular reviewer of several IEEE and IIT journals. So now I would like to request Professor Panda to start the session.
Yeah, am I audible, ma'am?
Yes, sir.
Yeah, thank you. Just confirm me if the screen is, if the PPTs are changing.
Yes, sir. Yes, sir. It's absolutely fine.
Okay, thank you. Thank you for the introduction. So, good morning
Nice.
to one and all. Uh, I hope the participants have gone through different lectures on solar photovoltaic system or microgrid systems throughout this workshop. And I'll be touching upon a different topic, that is multi-level inverters. And during this talk, we'll see not only the converter part, also the control aspect, right? So there are different types of control that has been recently in the recent year that has been proposed. So we'll see how this one of the control what I have picked up is selective harmonic elimination control. There are several other control schemes possible for the multi-level inverters, but specifically why I have chosen this, because as per the workshop which is planned, which is on the AIML, so selective harmonic elimination control is one of such control scheme which can take into account different types of optimization algorithm that has been recently developed, and so that it will be a good area where you can also focus in your future research. So throughout this talk, I'll be moving through for multi-level inverters, where I'll also discuss about what are the different types of multi-level inverters that are coming into this in the last few years. We'll see how different types of inverters, such as switched capacitor type inverter, that is more suitable for the photovoltaic system, that can be developed. And I'll ensure that at the end of the talk, you will appreciate that there is something that could be done on the inverter part, right, which is in heart of the photovoltaic system. We'll also see how it can be designed in simulation and in the real time. So as we all know, like I said in the first, in the photovoltaic energy, one which is one of the leading source of power, right? And in this area, why there is so much growth happening? That is due to the power electronic converters only, right? So power electronic converters such as this, what I have shown here, I think this is a very basic block diagram where this photovoltaic power is being fed to the grid through some converters, right? So one of the primary converter is DC-DC converter, which is used generally to boost the voltage, and then we generally use an inverter, right? Then in this circuit, if you can see, there are some filters and transformers are available, which is used to connect to the grid, right? Now there are also single stage system possible where this DC-DC converters can be completely avoided. Now if you want to avoid a DC-DC converter, so this inverter should be capable of boosting the voltage, right? If you use a general conventional inverter, either it is a single phase, this is a single phase system I've shown, the same can be extended to three phase system also. If you see for a single phase and three phase system, without a DC-DC boost converter, if you want to employ just the inverter, then this inverter should be capable of boosting the voltage, right? Where if you avoid also the transformer, now there is a critical aspect what you need to focus on, right? Here I have used a transformer. Now you think of, if I want to also remove this transformer, right, from the grid side, so I mean to say, if you try to design a transformer less system for the grid connected application using this photovoltaic energy or any other renewable energy source, then in that kind of system, the inverter should be capable of boosting the voltage, right? Otherwise you cannot efficiently utilize the solar photovoltaic power for the grid. So we'll see how a system can be designed, or how an inverter can be designed, a new inverter which itself is having the boosting capability without increasing much complexity into the system, right? So in this area, one new power converter came up in during 1900 century, where this multi-level inverters, right? Multi-level inverters which can produce a high quality voltage output. in this output side, if you see a general conventional inverter, right, that can produce a 3-level output generally, right? Initially we have 2-level only inverters, then we have moved to 3-level inverters like this. So if you see this kind of application where using multiple number of switches, you can actually produce a 3-level output from a conventional inverter. So this 3-level output is known to everyone, where it is a square wave output producing this positive half cycle, right, and producing this negative half cycle is quite easy, right? Whereas now what multi-level inverter can do using this again multiple number of switches and multiple DC sources. Focus on this part where I have used multiple DC sources. Now, if you utilize this kind of structure in a photovoltaic system, right, each source has to be replaced with an individual photovoltaic panel, right? So in this case, what will happen, because these are all isolated DC sources, so all these are to be replaced with a individual photovoltaic panel. Now in this case, this the structure is very complex, right? When you have multiple sources in the structure, then controlling each of the PV panel will be very difficult, right? Still, we see some of the advantage here that we are getting a multiple step in the output. So if you focus here, this output what you are getting at the load side, or that is we are trying to fit to the grid, we are getting multiple steps in the output. So that is the reason we call it as multi-level output. Now, if you want to design a different types of multi-level inverter, what we can do, we need to first understand the basic conventional types. Where conventional inverter initially what is designed is the diode clamp type, or what we generally called as the neutral point clamp type, right? Where if you see there is a neutral point clamping on the DC side to this load neutral, right? So here I have shown 3-level structures only, right? These are not the multi-level one. Even you can definitely increase number of switches here to go into higher level. But if you focus on this neutral point or diode clamp structure, we have multiple number of diodes connected in series, right? So if one of the diode fails, then this is a major problem for this structure, isn't it? Because there are multiple diodes are there connected in series. If one of the diode failure occurs, right, then this series module is going to fail. Similarly, in a flying capacitor structure, that is also having some benefit, but the major problem, if you see this flying capacitors what I have used here, that needs to be balanced, right? You need to balance the voltage across this flying capacitor, otherwise this will not give you the exact required output. Whatever your desired output, that may not be obtained if you do not balance this capacitor voltages. So one of the problem what people have faced is voltage balancing across the capacitor, right? Then there is a modular type of structure what is possible. Why it is modular and reliable? Because without the use of additional these diodes or the capacitor what I have told, just by increasing the number of switches or this module, this is one of the module of the 3-level inverter, you can cascade this structure, or you can just go on increasing the number of level by cascading these modules, which are called as the H bridge modules, right? So if you design such a structure, that is called as a cascaded H bridge structure, which is one of the popular type of multi-level inverter. Now, by the end of this talk, you will realize what is the problem with even this. Even if you do not use capacitor, diodes, all these things, right? How the complexity comes into picture, that we'll see by the end of this talk, you will realize it. So this I've shown some of the application where industries are also implementing the multi-level inverters in their applications, right? Siemens, Rovicon, Alstom, Rockwell, all these have utilized different topologies even for photovoltaic power processing as well as for industrial drives. Different applications are there, but among these are the two applications which are majorly being utilized, right? One is the photovoltaic power processing, and the other one is the drives application. So in different types of application, you will find nowadays in statcom application, right, high frequency grid tied system application, you will find multi-level inverters generally. So let us see how we can design a multi-level output. To understand basics, I have shown here two H bridge module, right? One of this H bridge module is here consisting of 4 switches, what you can see, and one component, one simple DC source, right? As I have told you, this can be replaced with a photovoltaic panel, right? Now, this is another module, and let us consider several such modules are cascaded. So what we are going to do, the first module, let us say we are going to switch it on, because every module will produce a 3-level output, like I have told in the starting. 3-level output. So when we switch on these two switches diagonally, then obviously it is going to give me a positive output. And when you switch on these two switches or the other two switches, we are going to get the negative half cycle, right? So if you switch on this to this first module only, right, at an instant, which is, let us say, alpha 1. What is the alpha 1 I am taking here? That is the switching angle. So slowly I am trying to introduce to you how selective harmonic elimination, that was the major research topic what I have chosen today, how this came into play. So to understand this, you need to understand this output level generation pattern first, right? So if you see here, there is a switching angle I have taken alpha 1, where I will try to switch on my first module, right, or the first H bridge. So at alpha 1, what I'll do, these two switches, like let us say mark it T1, T2, I'll switch on T1, T2. And similarly, the T3, T4, the other switches, I'll be switching on here at pi plus alpha 1, right? Because this half cycle is pi, and this is your 2 pi cycle, full cycle. So within this half cycle, I have switched on this first, at alpha 1, I have switched on the two switches, and the other two switches I have switched on this at pi plus alpha 1. Similarly, to get a multi-level output now, let us consider like this, I have 4 number of modules, right? I have 4 number of modules. Now, out of these 4 modules, what I'll be doing, each module I'll be switching at a different instant, right? Like I've switched on the first module at alpha 1, the second module may be switched at alpha 2, the third module may be switched at alpha 3, and the fourth module may be switched at, let us say, alpha 4, right? So a different switching angle, I have tried to switch on the different module. But each module, what they are doing, each module is producing a 3-level output, as you can see here. These are from the different modules, the output is. So each module is producing a different, at different switching angle, it is producing 3-level output. Now what will happen, because I have connected all these 4 modules in a cascaded connection, right? Cascaded connection means what? The output, how it is connected, if you see, this point is sorted to this point of the other module, and the load is connected a common point between these two, right? So due to that, what will happen, the output voltage what you are going to get at the load side, now that will be a combination of the output of all these 4 modules, right? All these 4 modules, whatever output you have, that will be finally combined. So you will get a output pattern like this. If you observe this output pattern here, because of the 4 DC sources what you have used, let us consider these are the 100-volt panels. Let us say, simply I am taking, these are all 100-volt symmetrical panels. So you are going to get at the output 400 volt, right? 400 volt here, and you have got 4 steps in the output. So if you observe this output, which is going very near to a sinusoidal waveform, right? So because of that, what will happen, if I see my total harmonic distortion, a factor what is taken generally to evaluate the harmonics. So if you calculate the total harmonic distortion of this structure, then you will realize the harmonics is reduced from about 40%, which is generally in a 3-level inverter, which is very high, right? More than 40% even you will get. If you see this type of pattern, and if you realize the TSD, you will see that TSD will gradually reduce down to, let's say, about 20 to 25%. Even if it is reduced to 20%, I am talking about the voltage TSD, not the current TSD, right? I am talking about the voltage TSD. Why not current TSD? Because in this case, if this load is of, let us say, RL load, inductive type load, you will automatically get this current pattern, right? It lags behind the voltage. So you'll get a current pattern generally in sinusoidal form. So by changing the load pattern, definitely you are going to get a sinusoidal type of current. So I am more concerned about the voltage TSD, which is now coming approximately 20%. Even that is not suggested. If you see the IEEE standard, IEEE 5.9 standard, and there are many other standards are there. So if you see these standards, they have been clearly mentioned it. If you do not reduce the TSD to below, let's say in a single phase application, you must reduce to below 8% even, right? And similarly
Doctor,
for three, yes. Any doubt?
Sorry. Yeah. Yes, sir. I have small doubt in in second module, like
Yes.
when you're there is a between alpha 1 and alpha 2.
Yes.
So both the TN4 and the TN2 will be turned on, because if it is all the switches are open, then the potential at the center of those switches will be half of the voltage, because
Yes.
there will be a parallel capacitor across the switches.
Right.
Is it correct? Means both the TN4 and TN2 will be shorted. It will be like
No,
that
no, no.
pattern.
Right, right. I understood your point. I think some of the participants have been unmuted. Okay, right. So see, what you have asked is correct. I will go to this part in the next session. Right, in the next section you will see how the current flow pattern is. Like what I said, only two switches are on. For current flow path, you need to definitely turn on the other two switches in this module also. Right.
Okay.
If you do not turn on this module at all, then you will not get the full current flow path. But what I am trying to say, the firing angle that is given for this switch, right, is different from the other module switches. So this alpha 1, alpha 2 corresponds to each of the module what I am trying to switch on. But for the current flow path, definitely we are trying to turn on the other switch. We will clarify this concern after some time. Okay. So at that time you will be clear. So now if you see here how many switches I've used, because later on we are trying to also I'll highlight how a different types of inverter, because this is the very old one. The cascaded HBridge type converter is very old, and now we have come to a stage. If you see the last 2-year IEEE transaction papers, you will find out there is a different area of research in the multi-level inverter, right? And I will try to touch upon that area, how you can still produce a different type of multi-level inverter in new structure. You will be able to develop a new structure, right? So here if you see how many number of DC source I've utilized for the 4 module 4 DC sources, right? So it means I need 4 such panels. Then how many switches I've utilized here if I want to find out the number of switches? So if you see here 16 number of switches are required, because 4 number of switches in each module. So for the 4 modules you need 16 number of switches. So with 16 number of switches, the level what you are getting here at the output side, if you observe here, I am getting 4 steps in the positive, 4 steps in the negative cycle, and there is a 0 level, right? This 0 level is also very important. The 0 level will be produced like when you consider, let us say the upper 2 switches are turned on or the lower 2 switches are turned on. In that case, what will happen? The load current will circulate, right, in the load circuit itself. So due to that, this output voltage will be 0. So if you see this output, we are getting a 9 level waveform here. This is called as a 9 level waveform, right? Similarly, if I let us say consider 2 number of module, so in that case you will get a 5 level output using 2 modules, right? 2 steps in the positive, then you will get a 0 level, and 2 steps in the negative you will get. So you are going to get a 5 level output. So now you consider, for generating just a 9 level or a 5 level output, just to reduce the harmonics little bit, how many number of switches? The complexity is getting increased, right? If you consider an industrial application, the number of switch when it increases, definitely your cost, complexity, everything goes very high. So you need to focus on that part also. See, this curve shows that part only, right? For a diode clamp or a cascaded HB structure, if you compare the number of switches and number of DC sources or capacitor, you will find out how it can be reduced with increasing number of levels, right? We'll go into that aspect later on. Now, as I have highlighted you these points, alpha 1, alpha 2, alpha 3, what you have understood the switching angle. Now think about a multi-level output like this, what I have shown here, and at different switching angle like this, these are the switching instances, you are trying to switch on these modules, right? So how you will express this output voltage mathematically now? Mathematically, to express this output voltage, you need to definitely process through Fourier series, right? So if I do some Fourier series application here, I can write my total output voltage in terms of different components, right? Different component means like let's say in terms of alpha 1, alpha 2, I can write this output voltage. So here, if you see, I have considered only odd number of levels here, right? So this, what I've written here in terms of firing angle, in terms of the switching angle alpha 1, alpha 2, there are terms cos x alpha 1 or this cos x alpha p. So here I am considering that there are, let us say, p number of switching angles, right? P number of switching angles are there. So for that type of output, you will get this output voltage expression. Now, if I simplify a little bit, if I write only the fundamental expression for this voltage or the fundamental voltage, how this fundamental voltage can be expressed? That can be expressed in terms of this way, right? Where this 4 VDC by pi actually corresponds to the modulation index, right? We'll slowly understand that. And there are different firing angles here like alpha 1 to alpha p. Similar way, if I, let us say, want to calculate the second harmonic, I can write the expression. Same way, if I want to write for the third harmonic, I can write the expression this way, right? Where this things is going to change. This x is going to give me either 2, 3, right? If you're putting that value, you can write this expression definitely. But try to understand in this kind of pattern, right? What I've shown here, whether there will be a second harmonic, fourth harmonic, or which we call as the even order harmonics. So if you see this harmonic profile, what will happen because of this quasi square wave type output, where this positive half is equals to the negative half, mostly the second order harmonics, first order is the fundamental harmonic, but the second order harmonic and the fourth order harmonics will be not present. So here, what will happen, we may discard it. You will get only the odd order harmonics like third, fifth, seventh, ninth, right? The even order harmonics, if you analyze through a Fourier series, you are going to get 3 components, right? A0, An and Bn. So from this, if you see, like it is mentioned here, these components will be completely eliminated, which is corresponding to the even order. You are going to get only the odd order harmonics or the odd components. So now we are trying to focus on the odd order harmonics only. And from this odd order harmonics, again, if you see the harmonic profile, if you go to a 49th, let us say, order, right, you will see at higher order, the magnitude of the harmonics is very, very low. Definitely. From this harmonic profile, if you see, at higher order, the magnitude of the harmonics is very, very low. Whereas at the lower order harmonics, like third, fifth, seventh, ninth, these order of harmonics magnitude is very, very high. So our focus should be on these orders, right? If you want to even eliminate some of the harmonics, right? Like I have titled selective harmonic elimination, then these harmonic orders should be selected, which can be eliminated from the output voltage. So like I have told you, you can write expression for the third harmonic, fifth harmonic, seventh harmonic. But now you have to consider here how many number of switching angles are there. If I consider, let us say for the time being, I am considering a 7-level output. What do you mean by 7-level output? There will be 3 steps in the positive, right? And there will be similarly 3 steps in the negative. This is your alpha 1, this is your alpha 2, and this is your alpha 3. So there are 3 number of switching angles. Now if you consider these 3 number of switching angles only, and if you write such expression, you will realize by solving 3 equations, you can at least remove 2 unknown values, or you can at least find out. You can find out 2 unknown values, right? Or if you want to, let us say here, find out 3 unknowns are there. Alpha 1, alpha 2, alpha 3 are the 3 unknown variables, right? So if you want to find out 3 unknown variable, you need to formulate some kind of equation like this, which are represented as the harmonic equation, which are called as the harmonic equation. Here, as you can see, I have mentioned this is the fundamental equation. This is for the third order harmonic. Similarly, you can write for the fifth order harmonic. Similarly, you can write for the seventh harmonic, right? So this M I have represented for the modulation index. Like I told you in the last, modulation index is nothing but this, the reference value to this your value of this VDC1. In terms of VDC1, I have what I have written, that is in terms of the reference and the carrier signal, right? Here there is a fundamental carrier only. So here you are getting number of switching angles, right? All these switching angles, if you see this last one, what I have shown you, this waveform, the 7-level waveform, focus on this part. Here, this positive half cycle is limited to 90 degree. Oh, sorry, this is 180 degree. So the half cycle, if I consider only the positive half cycle up to this part is 90 degree, right? So all my switching angle like alpha 1, alpha 2, alpha 3 lies within the range of 0 degree to 90 degree, right? Or 0 to pi by 2. So that is what is mentioned here as a constraint now. So I am trying to formulate a constraint function here, right? Which is all the firing angles are within the range of 0 to 90 degree, right? So taking into account this harmonic equation and this constant function, can I write an objective function? Because my objective is very clear. I have to minimize the total harmonic distortion at the end, which I have highlighted in the starting. The total harmonic distortion should be low, so that your at this time when you are making the total harmonic distortion low, what you are focusing on? You are focusing on the low order harmonics only. What is this low order harmonics? Like I have told you, the third order, fifth order, seventh order, ninth order, these order harmonics, because the high order harmonics can anyway eliminated by utilizing a small filter. So for this total harmonic distortion to reduce, now the major question comes, can I take the THD itself as the objective function? Can I take THD itself as the objective function? So if you take THD itself as the objective function, right, you will not be able to do two things. First thing is that you will not be able to maintain this fundamental value, and at the same time you will not be able to eliminate the selective order of harmonics. Selective order of harmonics. Why you will not be able to eliminate? Because THD is a total sum of all the harmonic orders, right? In comparison to your fundamental value. So if you take THD as the objective function, that is not a right choice. So what I have done here, I have formulated an objective function which I have named as fitness function. This is nothing but the objective function only, where I have taken two components. If you focus, right, two components. These are, I don't know why it is not visible. So there are two components I have taken here. One is the fundamental component, which corresponds to this fundamental order of the harmonics, and this corresponds to the all other harmonic level like third, fifth, seventh, and so on, right? So for a 7-level inverter, let us focus on a 7-level inverter only, where there are three switching angles, alpha 1, alpha 2, alpha 3. So if you see these equations, which is a generalized equation I have shown, but if you see this equation, you will be able to get four such equations, right? One corresponds to the fundamental one, and four equations correspond to, let us say, your third, fifth, and seventh order, right? You can write, oh sorry, you will write three equations only, not four equations, right? So it means what? If you write these equations, you will be able to eliminate only third order harmonics and fifth order harmonics, right? You cannot concentrate on any other harmonic orders for a 7-level inverter. That is the problem with this. So you can eliminate the third order harmonic, fifth order harmonic. Now if you, let us say, if you take a 9-level inverter or 9-level output, so you have got four switching angles here, right? Four such switching angles here. In that case, what will happen? You can concentrate on third order, fifth order, seventh order. So it means that we have understood, as per this number of switching angle, right, you can get eliminate these lower order harmonics, but it is specific to a number of level. For a 7-level, you can eliminate only third and fifth. For a 9-level, you can eliminate the third, fifth, seventh order harmonics only. So that is how the equations are, right? If you have three such equations, you can you have seen such equations are there, you can find out the switching angles like alpha 1, alpha 2, alpha 3, and at the same time you can eliminate the harmonics. So what you are actually trying to do, you have to solve this objective function in such a way that now the order of harmonics what I have targeted, that will be eliminated. At the same time, I will get this constraint functions values like alpha 1, alpha 2, alpha 3, which I want, because that is needs to be supplied to this program, right? That needs to be formed. You need to form a lookup table. You need to form a lookup table where you will store all your data related to when there is a change in modulation index. From modulation index actually varies from 0 to 1. So when this modulation index changes from 0 to 1, what is the change in alpha 1, alpha 2, alpha 3? So if you store that in form of a table, that is what is called as a lookup table. Now this can be utilized to design your inverter, definitely, because you know the exact switching angle when my switches needs to be turned on. So to solve this now, to solve this objective function, there are different methods people have proposed. Initially, if you see in 1990s, there are some mathematical approach that is started. Mathematical approach like your Newton-Raphson, right? And there are different other methods are there. But these methods, if you see, they actually suffer from initial guess, right? They require an exact initial guess. So to avoid this problem, we have moved to this other type of approach, that is the optimization based approach. What we do generally in the optimization based approach, we can apply different types of optimization techniques. Like you might have studied about particle swarm optimization, right? And you have firefly algorithm, flower pollination algorithm, different such other genetic algorithm, and different such algorithms were recently being developed. Whatever recent algorithms are there, you can utilize these algorithms now to actually evaluate this fitness function what I have shown you, or the objective function. One more thing, if you focus on this fitness function, what it is done, knowingly I have raised the power to 4, and this order of harmonics I have raised the power to 2. So you need to understand, you can take both this uh, power of this fundamental as well as the individual harmonics order to 2 only. But why it is done specifically to 4th order? Because to put a penalty function. So what is this penalty function what I have chosen here? To give more importance that these fundamental components are very high, right? To give more importance to the fundamental values, I have raised the power to 4. Even if you see some of the papers where they have taken the power to 2, both this fundamental and individual order of harmonics, that is not a problem, right? This if you do, you may get some accuracy in the result. That is the reason these powers are chosen, right? Now if you see here, if you take any of these algorithms, you try to implement either any of these algorithm, what we have done here, different based on the different modulation index, I have tried to form a lookup table. That lookup table what I was just now explaining, which is nothing but corresponding to modulation index, what are my switching angles, and what is the total harmonic distortion correspond to this modulation index, let's say 0.1, 0.2. So same way, up to 1, if I moved in the modulation index, what is the corresponding switching angles? If I get these values, right, then I will be able to process through a switching logic decoder. Now one of the participant was asking me how you will switch on only the first module, because there will not be a path in that case. You will not get a path in that case for the current to flow, right? Because otherwise the other module will maybe short circuited. So in that case, what we have to understand, the switching pulse decoder, where you have written which switches should be turned on at what instant, that can be made very clear, right, in this. So what is this switching pulse decoder, we'll see again. So this kind of pulses what I've obtained, that can be given to the switches so that you will get an output. Okay. Are you getting a noise? Can anyone confirm me? From my side, are you getting any
No,
noise?
no, 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 no.
Is it fine?
Now getting a noise.
Okay. I don't know, there is some work going on nearby, maybe because of that.
Okay. It's okay, no problem.
Okay, okay. So, what till now I have focused on, if you see, the selective harmonic elimination control with the approach of any type of such optimization algorithm, you can actually eliminate the targeted order of harmonics, where the targeted order of harmonics are the lower order harmonics like third, fifth, seventh, ninth. These are the targeted order of harmonics, right? You can actually eliminate that so that the total harmonic distortion can be reduced, right? So we'll see some of the results after this, where the targeted order harmonics are eliminated. But just to show you a comparison, because what is the traditional practice, what we have done, traditional practice, what I mean to say, we have taken generally a reference signal, right, so far, and you have compared with a carrier signal. This is what we do generally for a pulse width modulation control. What we call it as sinusoidal pulse width modulation control, right? Similarly, what we do here, when you take a carrier and compare with a sine wave reference, you generally generate a switching pulses. So if you do this type of thing, what will happen? The output output pattern, if you observe the output pattern here, what I have shown you the output pattern initially, what is the difference? You can try to correlate with this. See this output pattern. This output pattern, if you focus, and this output pattern, what I am showing you now. What is the difference here? The output pattern, what I have shown you for a 7 level, right? This is also for a 7 level output, where there are 3 steps if you focus here. First step, second step, and the third step. So if you see this kind of output pattern, you will realize that this is a fundamental frequency control, where this is a high switching frequency control, is it not? Because of the carrier signal, you are actually doing high switching frequency. So because of this high switching frequency control, you will get this type of output. So PWM techniques, in a way, I have divided into 2 parts. One is this fundamental frequency control modulation technique, and this high switching frequency control modulation techniques, where you have generally a reference and a carrier. But in this fundamental frequency control, what we do generally selective harmonic elimination or a nearest level control, right? In this kind of technique, you will see this output per level, you will get only one single switching. Here if you observe, there is a single switching per level, but here there is a multiple switching per level, right? Here you have multiple switching per level. So because of that, what is going to happen, if you design an inverter with this kind of logic, definitely your power loss, total power loss, which is a function of your switching loss and conduction losses, so that is going to be very high, right? So with this control techniques, you can actually optimize the losses also, power losses. So this, just to differentiate between 2 different types of PWM technique, I have shown you this waveform, so that you will realize you can actually get this output in this way, where there is only one switching per level, or you can get this type of output where there are multiple switching per level. Both are correct. Where to implement, how to implement, that is your lookout. You need to first choose which technique can be easily implemented and where the power loss can be easily optimized, right? Now, let us see some of the implementation. What we have done is we have tried to compare 3 different techniques here, right? Let us not focus on this optimization technique, right? Because there are different other optimization techniques that is possible, and there are many researchers, they are working on different types of optimization algorithm. Let's say flower pollination algorithm is there, then teaching learning based optimization algorithm, gray wolf optimization. Likewise, there are different optimization algorithms. So you should find out the optimization algorithm and try to compare all these factors what I've written. All these factors. Try to see the first thing, the fitness function what I have shown you, the fitness function equation, where if you observe the fitness function using, this is one of the method which I have named as particle swarm optimization with fish swarm optimization combined. This is a hybrid technique. So if you see, with this hybrid technique, I am getting the least fitness function value. It means this is giving me more accuracy in the objective function, because objective function is minimized to a very accurately using this technique, right? So it means that this is going to give me some exact accurate output. Whereas compared to the particle swarm optimization or the other technique what I have chosen, the conventional fish swarm optimization, I am getting some better output here or higher accuracy. But here with this you cannot actually prove the accuracy. That's why I have taken another factor here. This is a distribution function. This distribution function, what it is going to give me with respect to the fitness function value, right? With respect to the fitness function value, how accurate you are. So if you observe it here, again, for this hybrid optimization algorithm, I am getting here, this is least value, right? The fitness function least value. And in this area, if you focus on, compared to the PSO and compared to the other optimization technique, we are getting a better output, right? Same thing if you now compare the total harmonic distortion, again you can get similar result. But observe it here, with respect to the modulation index, when modulation index varies from 0 to 1, what is happening here? The THD goes on decreasing, right? That is a fact that when modulation index increases, obviously the total harmonic distortion goes down. So if you see, you can clearly tell me that why we generally take, when we design the inverter, why we generally take high modulation index. This high modulation index we take generally where the THD is get very low, right? But if you see here the distribution of THD, as you can see at nearly 0.95, right, at this value, the THD is very minimum, right? And that is using this technique, that is using this hybrid technique, the THD is minimum. So corresponding to this value, what I am going to do now, because my THD is minimum at this instant, corresponding to this value, can I take the switching angles such as alpha 1, alpha 2, alpha 3, what I have obtained using the programming, can I take this into account to design my inverter? Yes. So that is what is shown here. This firing angle or the switching angles alpha 1, alpha 2, alpha 3, if you see here, that is also changing with respect to modulation index, right? With respect to modulation index, this alpha 1, alpha 2, alpha 2, alpha 3 keeps on changing. And that is the reason the THD also keeps on changing, right? So if you can see here, at corresponding to this 0.95, where I am getting the THD minimum, I have to take the switching angles, corresponding switching angles, so that at the same time, again, to focus on very important aspect here, at 0.95, whether our individual targeted harmonics, because here I have targeted, let's say, 3rd, 5th, 11th. You can also target 3rd, 5th, 7th, no problem. So whatever your targeted harmonic orders are, whether they are eliminated or not. So to sort out this, I have shown you a individual harmonic profile. So if you see, all the targeted harmonics are completely eliminated at this instant, programmatically. So using this programming language, what I have solved this, I have got this waveform that the individual harmonic orders are removed, THD is minimized at this instant, and I have obtained the switching angles. So if I form a table consisting of these switching angles and corresponding to the modulation index, that is what is generally called as a lookup table, right? So if I now store all this data in a lookup table, what I can do, I can simulate my any inverter design, and I can get a similar type of output like I have shown you here. Now you might be wondering, I have not done any simulation or explained any simulation. Don't worry, after some time we will go to the simulation part also, so you'll understand. Here I have just shown you an example output pattern of a 7-level output. See, try to focus on this part. What is changing here when there is a dynamic change in the modulation index? See this part and see this part. So here I have taken the modulation index is, let's say, 0.3. Here I have taken the modulation index approximately 0.6. Here I have taken the modulation index where my THD is minimum, right? I have taken the example, let's say, 0.95. So if you see, at low modulation index, the output pattern is changing. But one thing is obtained, the fundamental level is still maintained, right? The fundamental level is still maintained. And because of this change in switching angle, this alpha 1, alpha 2, and alpha 3, you are getting the THD, corresponding THD value is approximately 20%. When this modulation index is 0.6 now, you are getting a THD of 15%. So this is through the simulation, and the same thing can be verified here also in the programming. Right? When you have done the programming at 0.3, what is the THD you are getting? Right? Approximately 20% here, as you can see. So the same thing is verified in simulation here. Same way, when there is a higher modulation index, at 0.95, you can see here, the THD is reduced to approximately 10% for a 7 level. If you increase the number of level, then definitely the THD is going to reduce further. Same thing that is verified here experimentally also at 3 different modulation index, but they are dynamically changing. Through the programming, we have tried to change modulation index from 0.3 to 0.6 to 0.9, right? So this way, you can target the low order harmonics, and these low order harmonics can be eliminated from the output voltage of a multi-level inverter, right? I hope I am clear. And what you can do, you can actually apply different types of optimization algorithm, like I have shown you, any hybrid optimization algorithm also, to solve this fitness function. Once you solve this fitness function accurately, then obviously you are going to get corresponding switching angles. And for the corresponding switching angles, low order harmonics what we have targeted can be eliminated, and at the same time, obviously, when you minimize the low order harmonics, definitely the total harmonic distortion is going to be reduced. Here, if you have focused here clearly, these are the low order harmonics, 3rd, 5th, 7th, 9th, 11th, what I have shown you here. If you focus here, the 3rd order harmonics and the 5th order harmonics are slowly trying to get reduced. Even here, the 3rd, 5th order harmonics are trying to get reduced, right? So that is what happens when you target the harmonic orders actually accurately from an output voltage. Now, before I proceed to the next section, because in the next section I will try to now introduce a different type of structure what you can focus on in the multi-level inverter. Before I go to the next section, any doubt is there? Is there any doubt in this algorithm-based technique? Or should I proceed?
So, sir, a small doubt, like this is simulation part is okay, but before slide you shown a programming part. So
Yes, yes.
how it was done actually, how the these fitness harmonics are captured in the programming part, like can you try to explain, like?
Yes. Means you are talking about this part, right?
Yeah.
With respect to modulation index. That is what I told you, right? In the program, we have written this equation. The first equation corresponds to the fundamental, right? Fundamental order of harmonic. Second equation corresponds to the 3rd order of harmonic. And the next equation corresponds to 5th order of harmonic. Because I have written these equations in the MATLAB program, I will be able to obviously plot this 3rd order, 5th order. So that is what is plotted here. Each order of harmonic, 3rd order, 5th order, and this is the fundamental one. If you see here, the fundamental order is maintained at 100%. So if you write the equations carefully in the MATLAB, definitely you will be able to plot it. There is no such difficulty. Do you want me to show program or what?
Maybe when you're showing simulation, you can show. I
Yes.
think.
Okay.
Okay.
That time
Okay.
I might show you. Okay. Any other doubt? Okay. So if there is no other doubt, I'll proceed to the next section. Yes.
Good morning, sir.
Yeah. Good morning.
Sir, this experimental test that is done in hardware actually simulated the circuit or on any test ones?
No. This
That
is
is
for a
available.
specific multi-level inverter circuit. I will show you that circuit. This is for a 7-level multi-level inverter, right? For a 7-level multi-level inverter means let us consider there are 3 modules of a switch. That is what is designed in the hardware here in real time. And using a power quality analyzer, these harmonic spectrums are captured. This is done on a 7-level multi-level inverter. So I will go into that hardware part. By the end of this, we will realize. Any other doubts?
Okay. Master.
Okay. So let us go ahead and try to understand how to design now. Because there are some of the concerns like I understood how to design this multi-level inverter now. Because control aspect is clear, but how to design this multi-level inverter if you do not realize, then we will not be able to do it. So initially, if you see one of our review papers, you will realize there are different types of multi-level inverters here possible. And what happens, these sources, just in these sources, do not try to concentrate on this complete module. These sources what I have shown here, and the same module is repeated here. That is what is shown in the graph. You can go on repeating this module. What it has been done, you see this is a 100-volt, let us say, source, and same way for each of the module I have used this 100-volt sources. So if you see all these sources are same value, then this is called as a symmetrical type of multi-level inverter. And what people have focused on for the same 5-level or 7-level inverter, if I make these sources asymmetrical, what do you mean by asymmetrical? Now it's some ratio. Let us say this is 100 and this I am taking as 200. So what I can do actually, if you realize, using this first source, can I produce my first step output 100-volt? Yes. Then using only this second module, can I produce the 200 level output? Yes. And if you add these two, then you are going to get the third level also. Now you might be considering with 100 volt and 100 volt two sources in a symmetrical structure. How many levels are possible? You get two levels only, right? But you see now with asymmetrical source, with the levels are getting increased. That is the reason people have tried to design asymmetrical type of multi-level inverters, where this asymmetrical type multi-level inverters are actually designed with a focus on increasing the number of levels while trying to reduce the number of switches, right? This type of structures are generally named as reduced switch type multi-level inverters, where you can actually do asymmetrical design. But still, one of the major problem exists, what you should not forget, that I have highlighted in the starting. If I replace this with a photovoltaic panel in the real time application, just think about it, still you need multiple number of panels, isn't it? If there are multiple panels, controlling each panel, each converter is again getting difficult, because this photovoltaic panel cannot be directly connected here. That is connected through some DC-DC converters generally, right? If you think about it, think about controlling each of the DC-DC converter and each panel for tracking the maximum power. That is very difficult. But anyway, these structures were initially developed in the 1990s and in the before like 10-15 years. If you see the research what was going on, that is on this type of structures, which is consisting of multiple number of sources only, right? Multiple sources. How this one of the structure is designed, will do that, don't worry. But before we go into the design of what is the new structure coming into play in the last few years, 4 or 5 years, what is designed, I'll do that. But you see this structure I have shown here again as an example, a 15 level structure, right? You might be thinking that if it is a 15 level structure, then definitely it is going to give me very reduced harmonic distortion. Yes, but on the other hand, if you see, there are multiple number of sources connected in the input side, and all these sources are considered asymmetrical. These are not also symmetrical, asymmetrical sources. So controlling individual PV panel and maintaining this total voltage here across this output of this wherever it is required, that is very difficult, right? But what I have focused on initially, I have also worked on this part, where if you see this structure, I have used only 10 number of switch. 10 number of switch. If you compare with a cascaded H-bridge structure, right? Anyone can tell me how many such number of modules are required to get 15 level output? Like I have shown you, for a 7 level, you need 3 modules. So there are requirement of 12 switches. For 9 level, you need 4 modules. So there are requirement of 16 switches. Think about 15 level. How many such modules are required for a cascaded HB structure? I am talking about
7 modules.
7 modules. So if you have 7 modules, means 28 number of switches are required. But here, this is being done only using 10 switches to get a 15 level output. But if you realize, whatever the available source I am having here, the same output I am getting here, isn't it? I am not trying to boost the voltage. Instead, I am just increasing the number of levels while reducing the number of switches. So that is what is the advantage of this structure. So initially, people have thought about only designing reduced switch structures. So I'll show you some of the output here. This is one type of what is the control logic. I do not want to focus more on this, but you can refer to this one of our paper, where we have developed a closed loop control for controlling each of the PV panel. And in the real time also we have tested it. Here you can see that this is a high switching frequency control. Now you can correlate what is this high switching frequency, what is fundamental frequency. Fundamental switching frequency, like examples I have given you, selective harmonic elimination or the nearest level control. High switching frequency PWM control is where you have a reference signal and you have multiple carrier signals, right? So if you see this, this is one of our real-time design we have done. We have used some of the IGBT switches along with a solar simulator is used here. So see this output. We are getting this output at different modulation index. At 0.5 modulation index, we are not at all getting 15 level output. Why? Because I told you, when you have a reference and you have a multiple carrier signals to compare, you will lose the levels here, definitely when the modulation index is low. That is the reason we keep modulation index nearly equal to 1. If you keep the modulation index very low, you will realize that the levels are lost, right? The levels which is desired.
Means I am actually trying to get a 15 level output. Instead, I am getting here only 9 level output. So that is the problem here when you operate an inverter at low modulation index. But this problem may not happen if you do it with selective harmonic elimination control. Why? Because at selective harmonic elimination control, one of this, what we have observed, fundamental level is maintained. Fundamental level is always maintained. So that is how we have taken this voltage THD and the current THD, both is shown here. No doubt the total harmonic distortion in the current is reduced to 1.8% only. And at the same time, if you see the voltage THD, that is also reduced to less than 5%. So it can be easily connected to the grid, right? And that is what we have done it, grid connected inverter test. And these are some of the tests we have done with varying the solar insolation through the solar simulator. In the solar simulator, when you change the insolation or irradiation from, let us say, from 1000 watt per meter square to 600 watt per meter square, you will realize that the total voltage is reduced. So at the same time, when there is a change in irradiation, you can see the grid current is changing. The grid current is reduced here without affecting much to the desired 15 level output of the multi-level inverter. And this is another test conducted where there is a sag, grid voltage is reduced, and proportionally there is an increase in the grid current, right? Why I am trying to go fast here, because the new type of inverter what we are trying to focus now, that needs to be understood. So we will not put more focus on this part. How these tests are being conducted, we will realize. So now coming to the important research part, what is being done in the past few years. In the very recent past, if you see, people try to avoid this kind of structure where there is a requirement of multiple number of sources. Multiple number of sources is the biggest problem. Why? Because you need to control each PV panel, each of this individual DC source, right? So now, if you remember the first thing what I have told you, if you try to avoid this thing, your inverter should be capable of boosting the voltage. Otherwise, you cannot efficiently connect into the grid. So can we design an inverter which can itself inherently, right, itself boost the voltage? And when you think about boosting the voltage, you might think of actually utilizing inductors, right? But in that problem, what will happen when you utilize inductors? Right? The size of this inverter again goes high, and that is what we do generally in the DC-DC converter. We generally utilize an inductor, switches, and diode. But without this common use of inductor or transformer, can you boost the voltage? So that is what is the target here. So we'll see how it can be done. It means you still want to produce this type of level of multi-level output, but just using the inverter stage itself, right? Using single input. If you see here there is a one only single input I have used here. So this can be very beneficial for your use. How we can do that? To understand, I have shown here one of the structure again. See here, I have taken a symmetrical structure. So far we have understood what is symmetrical, where we have two number of sources all equal, right? Now you will realize how it can be done. Let us say this is 100 volt, this is 100 volt. So what is the output you are going to get? If this is the first H-bridge module, which is, and this is the second H-bridge module consisting of another 4 switch. So now you see the operation that is shown here, how the switches are conducted. But if you see, I am getting first step using this first module. Let us say I am getting here the first step output, which is 100 volt. And the second step output I am getting when I add these two. When I add these two means by cascaded connection I am actually getting here 200 volt output here, isn't it? Right? Now this is structure which is producing 5 level, because 2 level in the positive, 2 level in the negative, and there is a 0 level. So you are getting a 5 level output using how many switches you have used? 8 switch. And how many DC sources you have used? 2 number of sources you have used. So initially what people have thought about, what is this reduced switch type inverter? Like I have just now shown you. Initially people have thought about reducing the number of switch only. How we can reduce the number of switch? So can we do something like this? Because Anyway, you are trying to add these voltage sources. So can we do something like this, where there is, let us say, two sources I want to add it. I am putting them in series, right? And I am utilizing only one single H bridge. Focus on this design, what I am trying to do. The switch representation, what I have shown here is very simple. This is all having an anti-parallel diode. These are all MOSFET switches or IGBT switches you can utilize. Now let us say I have used only one H bridge, right? But at the same time, what I've done here, I have used two DC sources again, which are of, let's say, what is that, supply voltage 100 volt. And what I've done, let us connect another switch here. So what I'm trying to do, let us say this is your first DC voltage source which is working. So how your output will be in this case? So you will get an output just by using turning on this switch. You will get an output in this way, 100 volt, first step. When you now turn on this switch and you turn off this switch, what will happen? These two sources will be added together, right? So because of that, your output pattern, what you will get is the same 5 level output. See here, the same 5 level output can be obtained, but at the same time, what we have done here, we have utilized only 6 number of switch here, instead of this 8 switch what we have used earlier, right? And you have also, I have highlighted you one more important thing here. Two sources are there. Even here there are two sources. So you have reduced the number of switch actually, but the complexity in control is not much reduced. Why? Because you still need to use two different PV panels for these two different sources. What further we can do is the boost type inverter, or how it is designed, or the new type of structure what is coming into play nowadays. We name them generally as switched capacitor type inverter. Switched capacitor type inverter, what they can do, if you see here, now see this structure, I am just little bit trying to modify this structure. What we'll do, let us do the same thing. I am keeping one source here, but and the other source I am trying to avoid, and I keep a capacitor here. Okay, so now look at here what I am trying to do. So here I've used one DC source and I've used one capacitor instead of other source. And here what we can do, I have to keep another switch. I will tell you why I have to keep. Now what we can do, just to allow this first DC source to produce the first level, because anyway I want to get my level when this first DC source is there. First DC source means, let us say this is your only DC source here, not the first, only DC source. I want to get 100 volt output first. How to get 100 volt output here? So to pass this 100 volt, because I cannot go through this path, through the capacitor it will go. That's why I'm putting a simple diode here. Initially people have utilized switches also, but then it is realized that there is no need of switch here, because we will see why there is no need of switch again here. So initially what will happen, the current will flow through the source, through the diode, through these switches, through this path. So what is your level of output you are going to get? You are going to get a 100 volt output. Is it? At the same time, if I turn on this switch also, what will happen? If I turn on this switch also, this current what is going from the source will also pass through the capacitor in this way, right? So because of that, this capacitor is now coming in parallel to the source. So what will happen? Due to this parallel connection, this capacitor will now get charged, isn't it? And after a very instant, let us say this is your switching angle alpha 1 and this is your switching angle alpha 2. So at alpha 2, what we will do? Now we will turn off this switch. Let us say I will now turn off this switch, okay, and I will turn on this switch. If I turn on this switch now, my current will flow from the source again, and because the capacitor is charged earlier, so to what voltage it will charge? If this is 100 volt, this capacitor will try to charge up to 100 volt, right? not at the very fast instant, but after some cycle of running, definitely the capacitor voltage will rise to 100 volt. So what will happen? The total voltage will now be 100 plus 100. So you are actually going to get now at the output the required 200 volt output, or I can say 2V. So you see here, interestingly, I have obtained this 5 level output using just 6 switch. So I have actually reduced the number of switch compared to a cascade edge bridge. Using only one source, using only one, it means what? I have used only 100 volt in the source side, whereas I am getting here the 2 times this. So you now try to focus on this solar photovoltaic design where you have used a DC-DC converter. This DC-DC converter, if you are operating at 0.5 duty cycle, you will be getting the output approximately 2 times the input. Is it not? Approximately 2 times the input. So do you need a boost converter here? Do you need a boost converter here in this type of inverter? If you try to utilize, do you need a boost converter? No, actually we do not need it. Why? Because this converter itself has boosted the output to 2 times. That type of inverters can be named as boost inverter. But you might be wondering, if you use a capacitor, who will balance the voltage across the capacitor? Like I have highlighted in the starting itself, there are structures which is possible, like flying capacitor structure. Whenever there is a capacitor comes into play, you will have difficulty in balancing the voltage across the capacitor, right? But here you see, initially in the first level, when the capacitor gets charged in parallel, in the next immediate level, this capacitor is discharging in series with the DC source. So due to that, what has happened, the series parallel charge discharge pattern is maintained in each level. Same way in the negative half cycle also it is getting charged and discharged. So because the capacitor charging and discharging time, that is what is most important to design. The capacitor charging and discharging time is much lesser than the total output voltage. You will maintain the capacitor voltage throughout the output operation. If you see the capacitor voltage, it will be maintained at the 100 volt with some voltage ripple definitely. There will be some voltage ripple definitely, but it will be maintained nearly at 100 volt. So, do you need any voltage balancing circuit for the capacitor? No, you do not need. This type of circuit for that purpose is known as self-balanced switched capacitor type multi-level inverter. So I have got the multi-level output like I have desired. I have used only one single input source. I have boosted the output, and the capacitors also what I have utilized are self-balanced type. So I do not need actually a voltage balancing circuit or a sensor or auxiliary circuits to maintain the voltage across the capacitor. That is what is the beauty of switched capacitor circuits. So that is what I have tried to show here through this circuit. Now you can realize how this circuit operates, right? How we have moved from a higher number of switches to reduce switch type, but reduce source also, right? So this is how it is started with the design of switched capacitor type structure. So initially, what just before 2 years, people have also tried to again this module what I have explained just now using 6 switch. This is now cascaded. If you see here, again people have tried to cascade this structure, like we do generally for a cascade H bridge. But the fundamental beauty of this circuit is lost, isn't it? Because here again you need to utilize multiple number of PV panel for this. No doubt this is going to give me 9 level output, where in general using 2 H bridge you are getting 5 level only. Now these 2 bridges will give me 9 level output. Why? Because this is going to give me 5 level and this is going to give me the other 2 steps. So the first 2 steps are for the first bridge, and the second 2 steps are for this bridge. So obviously I am going to get a 9 level output. So the number of levels are increased, but just to increase the number of level, I cannot lose my fundamental concept here that these sources should not get increased, right? The number of sources should not be very high. So taking this into account, this type of structure I have designed in the laboratory. This is one of the initial design what we have done. Only one single input source is used here, if you see. And I've used 3 capacitors here. But these capacitors, again, like I have shown you the example, these capacitors are getting charged and discharged in a different fashion. It means what? You see here, in this first level, let us say, this capacitor is getting charged. But at the same time, I want my output also. So that is how I've done my connection. And the other level, if you see, this capacitor is getting charged from the DC source. But if you see the charging of this capacitor C3, you will realize that when I am charging the capacitor C3, when I am discharging these two, both capacitor and the DC source. So when these two capacitors are added together with the DC source, you are going to get 3 times, definitely 3 times the input voltage, isn't it? So this capacitor is actually getting charged to 3 times the input voltage. And that is the reason, using only single input source, here I am getting 6 times the output voltage. 6 times. It means what? This voltage is, let's say, V. This capacitor these two capacitors are charged to V and V, whereas this capacitor is charged to 3V. So if you now add it all together, you are going to get 6 times the input voltage. So there is a 6 times gain voltage boosting you have obtained for a 13 level structure. For a 13 level structure. And if you see the total number of switches what is used here is only 13. So using 13 number of switches for a 13 level, generally for a cascaded H bridge, you need 24 switches because you need 6 number of modules. So here we have, compared to a cascaded H bridge, we have reduced the number of switch. We have also reduced the number of source because only one source is there. So the control complexity will be very low. So if you see, these are the simulation output. Let us go to some of the real-time output here. For this circuit, what is designed in the real time, you see this capacitor voltages, which are naturally balanced. Naturally balanced means they are not requiring any type of sensor. These capacitor voltage VC1, VC2, VC3 are balanced as desired. So because they are balanced at the desired voltage, I am getting a 13 level output. Now see this output and see this output. Can you realize what is the difference between these two? Even this is a 13 level output, this is a 13 level output, where this output voltage is changing, because this is the first case is with fundamental frequency, and this is with the high frequency PWM control, where you have a sine wave and a carrier. Because we try to validate this with both type of modulation schemes, we have compared them. And here if you see, we have done dynamic change in the load. At this point, if you see, the load current is resistive, R load is there, but here we have done it with RL load. When there is an inductive load coming into picture, if you see this current pattern, it is more or less sinusoidal. This is another test conducted with change in frequency, right? When there is a change in frequency suddenly from, let us say, 50 hertz to approximately 150 hertz even, what is happening? What is going to happen? That is what is tested here. And this is another test conducted with non-linear load, like diode bridge rectifier. You can use a diode bridge rectifier to see the pattern of the output, right? This is the result obtained from a power quality analyzer for a single phase structure. If you see here, this is considered under a RL load case. So for a RL load case, this voltage, current, power, all these factors are taken because we want to test the efficiency. So if you see here, efficiency is approximately 95%, and the voltage TSD for a 13 level output is reduced to 3.8%, which is quite low as per the recommended IEEE standard. Here the losses are evaluated, and losses again are evaluated for both the schemes, for the fundamental schemes and for the high switching frequency control. If you observe it here clearly, for a high switching frequency, the switching loss is quite high. But for a fundamental frequency switching, the switching loss is quite low. That is what I have highlighted in the starting itself. When you do this type of control with a reference and with a carrier signal, definitely the switching frequency is high, so the switching loss will be very high. That is what we have verified here with respect to change in output pattern, that switching loss is very, very low for a fundamental frequency switching. This is the characteristics obtained for efficiency with respect to different change in output power. So we have changed the load actually. With respect to change in the output power, you can see the efficiency change because the power losses are increased. The efficiency little bit drops, but still it is maintaining more than 94%, right? So this is how you can actually evaluate an inverter. But again, there is a suggestion here. That suggestion we can see how we can still improve. One of the major factor when you design, now so far you have understood, is the number of DC source. Number of DC source is a factor which you need to concentrate on reducing. Number of switches is another concern. Power losses is a concern. Efficiency is a concern. These are the different types of different things you must take into account when you design an inverter. Apart from the control scheme you may utilize different types. For designing an inverter, these are the major things, but you are not considering a factor which is the voltage stress. So when you see across this switch, what is this voltage stress? When the switch is off, actually you will get a voltage across these all switches, whatever I have utilized here. So if you measure the voltage across this switch, you will see the total voltage add up to a factor called as total voltage stress. Sometimes this is also called as total standing voltage. Both are same. You mention it as total voltage stress or total standing voltage. Both are same, because in different research paper they have mentioned in differently. So this factor is going to impact hugely in your design. So you must consider a factor of this total standing voltage or total blocking voltage also, sometimes it is called. When you design, the switches rating needs to be chosen very carefully, right? Otherwise you will definitely going to incur more loss, power loss. So the voltage stress across the switches in a multi-level inverter specifically is different. If you see what is this voltage stress actually, if you see a conventional 3-level inverter where there are only 4 switches are there. So if you see if you see this, when these 2 switches are conducting, the other 2 switches are off. When these 2 switches are off, at that time, how much voltage it is actually blocking? It is actually blocking the same input voltage V, isn't it? So the voltage stress across all these switches in an H bridge, I can write that is total V. If I calculate the total standing voltage, it will be 4V now, because for the 4 switch. But this doesn't happen actually in a multi-level inverter where there are multiple switches operating at different voltage level. So what happens in that condition? This total voltage stress needs to be calculated or evaluated, so that you will realize actually this structure what I have just now shown you, with just because these capacitors are charging to 3V, when this switch is turned off, at an instant, let's say this switch is turned off, at that time this switch will have a voltage blocking up to 3 times the input. So it means that the rating of the switch is now going to change, how you choose in the real-time design. So that's how you need to evaluate the voltage stress across each of the switch first individually. Then you realize that a new structure needs to be designed. This is what we have done it here. We have designed a new structure using just 12 number of switches. Switch count we have reduced, but at the same time we have tried to keep this factor, the total voltage stress, very low. That is how this is the another design we have done it here. And we have tried to design in real time using this number of IGBT switches, a DSP controller, and a driver circuit is there for processing the pulses, switching pulses. If you see, this is again utilizing only one single DC source, but we are getting 3 times the output. Now I understand that you cannot get this how it is doing it for the 3 times. That's why I'll give you the reference papers, you can go through it. You can realize that time, because all the switching patterns are shown there. Because of lack of time, I cannot go through each of the switching pattern now, but this is an example switching pattern. If you see, when I am trying to generate an output for a specific level, at the same time I am charging some of the capacitor, and these capacitor do not require any additional sensor or voltage balancing circuit. That's why these are self-balanced type capacitor. And using just this capacitor arrangement that are called as switched capacitor, I am trying to boost the voltage from, let us say, 100 volt to 300 volt. That is what is the requirement here. At the same time, the voltage stress, what I've highlighted now, across the switches are kept very low. So that in a new design, when you try to do a new design, these are the factors you must consider, right? So these are the positive, negative levels it is shown, and a comparison is being shown here. If you see, with very recent structure, and these are all switched capacitor type design published in the last 2 years only, from the 2022 to 24. In the last few years, if you see, these all structure, they utilize single DC source only. So they are not trying to focus on the multiple source.
But at the same time, the switch total number of switches is quite high in some of the structure, whereas this proposed structure what I've shown just now, the switch count is reduced. Similarly, the other factor like diode, capacitor, these are used, but the voltage gain also is an important factor in some of the structure. These are all comparison for a 13 level structure. So for a 13 level, see, some of the time you are getting 6 times, sometime you are getting 3 times gain. But the voltage stress factor, if you see, like I have told you just now, this voltage stress is quite low for this, because that was the focus here. So you may focus on any of the part, any of the component, like I've told you, number of switches, number of sources, but try to optimize the design. Then only you will have a best circuit design possible for a real time application perspective. So because there are many factors here, you may not get a fair comparison. That's why there is a cost factor chosen. This cost factor is going to give me a real time value actually. What is the optimized parameter, what I can say. So the cost factor, I've shown you how it is calculated, taking into account every other factor. We have calculated a cost factor, which is showing me that the cost factor for the proposed design is very, very less. So this is how you can actually get best design possible in an inverter. So these are some of the results we have shown here again with the change in load dynamically. You can see here the load is changing. When the load is changing, you should see that the fundamental idea of getting the output voltage is not disturbed. Only the load current is getting changed here, isn't it? At the same time, see the required capacitor voltages. The capacitor voltage definitely having some voltage ripple here, if you observe, but they are maintained at a desired voltage of 100 volt. And same thing is done for a this circuit also, where you have tested this inverter with fundamental frequency like selective harmonic elimination control, also with high switching frequency control. Under both this condition, if you see the output pattern, right? If you see the output pattern, you can realize it is able to operate easily or smoothly with maintaining the capacitor voltages. This is again a real-time test conducted to evaluate that how much is the efficiency with different loading conditions. When there is a change in load, how much is the change in the efficiency? That is what we have tested here for a 13 level design, right? How you can verify there is a change in load? Because you can realize here there is a change in the active and reactive power. So that is how when there is a load change occurs, you can actually check the efficiency and other parameters. These are the results for the same circuit under grid connected mode. When you connect to the grid now, you have to test under, and when you have a solar panel actually in the input side, we have used a solar simulator, which is available in the laboratory. And from the solar simulator, if you see here, the irradiation is changed or reduced. Here there is an increase in the irradiation. Under both this condition, if you see, this is the grid current which is only changing. Whether our required grid voltage is maintained, and obviously the inverter output is also maintained. Why? Because the DC voltage from the solar panel is maintained at the desired value, right? And other tests are conducted for power factor change, when there is a lagging power factor and when there is a leading power factor. You can compare with the grid voltage and grid current. You can realize that, and when there is a unity power factor, the inverter is still able to produce the 13 level output as desired. So it means that you can actually design this type of test. My focus is not to show you only the test conducted here. The thing is that if you see, go through some of the paper, you observe the change in these results. What is the change happening? And when there are dynamic things are tested, when the dynamic change means like this, I've shown you when the irradiation is suddenly changed here. When there are dynamic change happens, what happens in real time? So that needs to be evaluated properly. So evaluate these things. My suggestion is evaluate these things first in the simulation. Once you are clear, you can go for an experimental test. Now, before you go to again experimental test, there are many factors to consider. What is that? You need to do a proper simulation, proper power loss evaluation, right? Whether it is able to handle the resistive type load, inductive type load, capacitive load, non-linear load, all these things needs to be evaluated. And if you try to design a switched capacitor type design, you need to focus on self-balancing definitely. Why? Because you cannot again choose a controller for balancing the capacitor voltages. So this is the real advantage of this design, where you do not need actually voltage balancing circuit. And at the same time, you are getting voltage boosting. So there's total standing voltage or the peak inverse voltage. This needs to be focused. And apart from this, power loss, efficiency, all this thing, you must choose a control scheme appropriately. So the control scheme is the very important part where harmonics, power quality, these things can be improved, right? So this is how I think I have tried to do a justice on your understanding. You can now go to design a new structure along with a control scheme. But I know there is still a concern that how you can do still a simulation, how you can start with the simulation. So I'll get you into that. So before I go into some of the simulation part, I think we have got some time, right? Any doubt here? Any specific doubt?
Sir, I have one doubt. Like in this structure, we are eliminating the MPPT, or that MPPT is still there. Like we are trying
See,
to
sir,
eliminate
if
MPPT.
there is a solar single stage system, if you focus on a single stage system like this, let us say, you do not need to really eliminate the MPPT. Let us say this is a grid connected system. What MPPT is doing, MPPT will sense the voltage. We have connected an MPPT controller here also. Even we have used a conventional MPPT control. This is, let's say, your VPB, this is your IPB you are sensing. This MPPT control can be implemented both for the single stage system and for the two stage system. Don't think that if you have a DC-DC converter only you need MPPT. So even if you do not have an DC-DC converter, this MPPT control can generate a reference voltage, and this reference voltage can be actually utilized in your inverter control. If you want to go through the full control, you may go through the paper that is given there, right, with MPPT. In other case, when there is a DC-DC converter, what we generally do from the MPPT control, we generally directly produce the duty cycle. Instead of taking a reference voltage, we produce the duty cycle and give it to the switches for this DC-DC converter. Because this part is not there at all, you can take that as a reference voltage and integrate that into inverter control. But that part I have not touched upon. And if you want to get more onto this, you should refer the paper. Any other doubt? Are you clear what I've told you?
Sorry, sir, not clear, but
आज बोल दिया इनको, आज अलाउ कर दिया, कल से कुछ एंट्री नहीं बोलेगी.
Not clear in the sense, have you ever tried to implement MPPT controller in simulation?
No. It's like my query is that as it is like suppose already 3 times boosting is happening. Suppose
Okay.
my like a solar panel is at some 100 volts, something like that. So
See,
I can use the
MPPT is for a different requirement. MPPT is not for what is that controlling or boosting. MPPT is there for always extracting maximum power from the solar panel. Whatever
no.
solar panel you have used, even if it is 100 volt or 50 volt, you are extracting maximum power or not.
Yeah. From this inverter, like as a already it's boosting is happening, and can we do the MPPT algorithm also in this inverter and eliminate that MPPT? That's what my question actually.
Yes, that is what I have told you. For with you in the inverter control itself, MPPT control is integrated. MPPT control or the MPPT control integrated mean to say separately you do not need a converter. But MPPT control is as usual. P and or incremental conductance, whatever it is there, you can implement and generate a reference signal for the inverter control itself. But if you try to completely eliminate this MPPT, if you are telling about that, that is a different concept.
Okay, sir.
Yeah. If you are utilizing a PV panel any design, then MPPT should be there, right?
Yeah, it should be there, and I'm trying to
Yeah.
understand, means like see whether the possibility of integrating that MPPT algorithm also into
Yes.
this one.
What you can do, one of the suggestion I'll give you, first you design using a solar panel, DC-DC converter, and an inverter connected to grid. Okay.
Yeah.
Second thing, you do the same thing, solar panel, eliminate the DC-DC converter, just use the inverter here, connect to the grid. Do these two type of simulation first. Don't think about the multi-level inverter or boosting structure. Do these two things first. You will be very much clear with the MPPT part for a single stage and two stage system. Once you are clear with this, you can think about how it can be done for even a boosting structure. Okay.
Okay. Yeah.
Yeah. Okay.
Thank you.
Any other doubt? Okay. So if there is no other doubt,
one more query, sir. Like presently the grid tight inverters, like 300 watt to 1 kilowatt grid tight inverters, they're moving towards this multi-level inverters, or they're still at like a transformer isolated based inverter?
like different applications are there, right? Here, if you see from the last few years, people have tried to develop transformerless. Like I've told you in the starting itself, can we actually go transformerless? Because we have tried to remove the boost converter, no doubt. But at the same time, if you also remove the transformer, if you remember the first structure I have shown you, I have tried to eliminate the DC-DC converter and both the transformer. So it means you are trying to go transformerless. But if you try to design those kind of structure, you will actually realize a major issue there. Major issue is that let us say you have a PV panel and you have this inverter structure, whether it is multi-level inverter or any single stage inverter. If you try to avoid this transformer also, between this PV and this grid side neutral, right? Grid side neutral, there exists a parasitic capacitance. So what will happen is through this grid negative, grid neutral to the PV side negative part, there will be a flow of leakage current. This is called as a leakage current. That is flowing because of the common mode voltage issue that arises. Okay. So this, in all the inverter, what you see for a solar connected inverter generally, you generally have to focus on the common mode voltage, evaluate the common mode voltage. Then you realize the leakage current is very high. But actually IEEE has recommended that the leakage current should be very lower than even 300 milliampere. Getting it? This leakage current should be even less than the 300 milliampere to keep it. Now what we can do? Why this leakage current can come into picture with a very high magnitude, you need to understand. Because you have avoided the isolations. Because the transformer or the DC-DC converter on this side was actually providing isolation. Now there is no isolation in your system. That's why the leakage current magnitude will go very high. So now in this kind of structure, what we can do further? The structure, what I have told you, you can actually boost the voltage. So avoid the DC-DC converter, avoid the transformer, and you have removed it. If you have removed it, there is no isolation at all. The leakage current will go very high. This is not recommended at all. So you cannot actually connect your PV panel to grid in this way. What could be done? Even if there are many papers, research work even is there in the literature, but there is this problem, the leakage current problem needs to be avoided. So one of the suggestions that we have worked in the past, again 2 years, we have different types of paper on this area also. That is called as a common ground structure, right? Common ground structure is one of the recent area what is emerging. So you can actually try to design an inverter which is having common load and source side connection. If you want, I'll show you some of the example. Common load and source side connection if you do. So because of this common grounding, what will happen? The leakage current, what I am talking about, will go nearly equal to 0 because of the direct short path, isn't it? So this I am leaving it up to you because of the lack of time. But you can actually search, go through my papers also. There are now very recently, whatever papers you will see, all these advantages need to be retained. All these advantages what I have told you: single source, voltage boosting, self-balanced capacitor, right? Control scheme should be effective, power loss should be low, voltage stress should be low. All this, along with all this factor, now there is another challenge I am putting on to you to design a common grounding. To design with common, like we do it for generally for a DC-DC converter also we do that. Like for a DC-DC converter, if you see, we call it as a common ground architecture, where this load side negative is connected to the source side, right? It is sorted. So you try to see some of the papers on this common ground area, then you will actually realize how this type of structure can be utilized for the photovoltaic system. Okay.
Yes, sir. Yeah.
So I'm leaving this up to you to mark it, because common grounding, again, if I start one common grounding, it will take more time. So let us go to some of the aspects in simulation or hardware, how we can start with. Not only in simulation, even in real time, how you can start with. I have shown here a simple controller, right? You can work on actually DSP board, FPGA board, or if you have in your institute available of DSpace, right? DSpace is there, you can work on that, or any type of FPGA, Cyclone, Ultra Cyclone FPGA, or we have worked on also Xilinx FPGA. There are many types of FPGA you can work on actually, right? Similarly, you have different types of DSP board like 28335 is most widely employed. That also you can work with. DSpace is advanced type of what is that controller available generally in the laboratories, where actually you can start with directly implementing your control logic. But here I have shown you a simplest controller, that is Arduino controller. Why? Because today's target is different. I do not want to develop a very complex control scheme. My target is to store the switching angle in form of a lookup table here and generate the switching pulses from the digital input output pins, right? That is what is my target. Are you getting it? I want to develop this controller in such a way that I want to store in form of a lookup table. Lookup table means, again, with respect to modulation index, the switching angles, alpha 1, alpha 2, alpha 3, whatever is there, that I am going to store it here. And accordingly, for each switch, I want to generate the switching pulse from the digital output pins. So to do that, what is my suggestion is, if you do it through Simulink, I think it will be much better for you. If you do it individually through using Arduino IDE, there is a software called Arduino IDE, even you can work on that. Because Arduino is generally employed for different types of applications. Robotics application, even you will see Arduino, or different other applications. So Arduino IDE is available where you can actually do the program. But I suggest you can directly do with Simulink itself. Once you do the MATLAB Simulink design, you do not need to go with this one. So what we can do, look at here, there is a software package available in the MATLAB itself. Just search in this name, you will get a software package. So with this software package, once you download in your MATLAB itself, a software package will be installed, right? This software package, or this is not a software package actually, Arduino hardware support package. When you do this support package installation, you will be able to get some of the blocks like digital input, digital output. These are all the block sets, right? Like in the library here, in your Simulink library browser. I hope all of you are clear with Simulink library browser, where you will get the block sets like this, digital output block sets, where it is asking you a simple question: what is the pin number you want to utilize? Can you see? So if I utilize, let us say this block, digital output block, because my requirement is I wanted digital pulse finally, isn't it? I want a pulse only. So what we can do, something like this. If you see here, this is the block I was showing you just now. In this block, I have only mentioned the pin number. What I want to do with pin number 13, I just want to check my output. So this is just to check first, not to implement your multi-level inverter switching scheme. This is just to check that whether the LED is blinking. So just to check, initially you need to test the hardware is integrated properly and it is communicating with your MATLAB, isn't it? So just to check the communication is proper, what I have done, there is a LED blinking test freely available. You can go to that, you can utilize that. And why it is given pin number 13, if you see this Arduino board actually, which is Arduino Mega board I have chosen, to this pin number 13 here, there is an inbuilt LED connected. This is the LED inbuilt. So you do not need an external LED also. To the pin number 13, there is an inbuilt LED which is already connected internally. So if you can switch on and off this pin number 13, you can actually realize the LED is blinking or not internally on the board. So if that is, communication is successful. And how you can do that? When you click on this build, this is an option, you will get it to build on the board. So what this build option will do, it will convert your model in Simulink model into a code, and that will be dumped into the controller. That will be dumped into your any controller, And same kind of thing you can also do with DSP boards, FPGA board. If you want to do with FPGA board, you can actually do with Xilinx. This is a very high-end controller, right? With Xilinx controller also you can do. But my suggestion is you can start with this one actually. Many of the places I've seen, the starting of the hardware is getting difficult. So you can start utilizing this type of things first. Then you can, if you have availability of FPGA board, you can do that definitely. If you have availability of DSP 28335, you can go with that also. Because there is a Code Composer Studio available for the DSP. You can work with this Code Composer Studio also. Now, what we have done here, just this board, I can test for testing inside the configuration parameter. This is in the Simulink itself. In the Simulink itself, I have done this setting where in the hardware implementation, it is asking me which board you want to choose. So I have chosen this Arduino Mega board. It is not that difficult. And I am giving this kind of pulse. I am generating this kind of pulse from the pin number 13. And I am checking it here whether my LED is blinking or not. That is what is my requirement. I want to test it. So if you test it here, you will get something like this. I don't know whether it is this video is not running. So there is a small video I have taken. You can see this LED is blinking. So it means you are now successfully communicating with the MATLAB and the Arduino board. Once you are successful in communicating, now you can go for designing this type of simulation. What we have done it here. If you see this simulation, I have explained you just before some time, where I have used only one single DC source, one capacitor, which is charged and discharged naturally, and we are able to get pipe level output, isn't it? Using 6 switches. Just now I have explained you this. Same way you can design 7-level circuit, 9-level circuit. There are many available circuits are there. Focus on that designs first. So you can start with this basic. This is the basic structure of all fixed capacitor type. That's why I have explained you this. So you can go on testing the capacitor voltages. You can go on testing this inverter with different type of load. With different type of load means when there is a sudden change in load from R load to, let's say, RL load. What happens? That is what I was showing you. When there is a change in load from R to RL, what happens? So first test in simulation, and the switching pulse logic I'll show you. First test in simulation that. To test in simulation, like this is a switching function I have developed here, right? This switching function is going to give me switching pulse for all the 6 switches. And if you observe it here, this is I am checking with the scope in the Simulink. At the same time, I have used this digital output pin, what I have just now shown you, digital output pin of this Arduino, where I have mentioned the pin number 31, 32, 33 up to 36, because there are 6 switching pulses, right, for the 6 switches. So if you observe it, from each pin I am getting the required output in the simulation. And the same thing now, definitely if you build into a Arduino board, you are definitely going to get the digital output pattern same way from the Arduino board. Once you are done with this, you can definitely go ahead, because the most important part is generating the switching pulses from the any controller. Once you are able to do with this, what is the next target? Target is to design the real time. If you are getting a controller board output pulses you are getting, you can have a driver circuit. What is the need of this driver circuit? Actually, it will amplify the pulses, because these controller board generally produce a pulse of 0 to 5 volt, which is not enough to trigger your switches, any of the switches, MOSFET or IGBT. So you actually need to amplify the pulses, and that amplification task can be done by a driver circuit. And that we generally do with TLP 250 based or TLP 350 is there. There are different type of Skyper 32 type of driver circuit is there for high-end design. Because I am going through a low-end design, you can work with TLP 250. Or if you want to design a very high power inverter design, you can go for Skyper 32 based driver circuits. Initially, people have also used MCT2E. These are the different type of driver circuits actually, which doesn't only amplify, it also isolate. What is the need of isolation? Because your inverter switches what you are trying to operate, that might be operating at 200 volt or maybe 2 kilovolt at very high voltage. This control circuit is operating at very low voltage, only 5 volt. So you must isolate them. That's why the driver circuit is work in two purposes, isolation, amplification. Once you are getting these amplified pulses, Now what you can do, you can give these pulses through the switches, whatever switches are there. So that is again through, without driver circuit it is not possible, right? For driver circuit again you need an individual isolated supply. So when you start designing it, you will realize this. So this is the kind of what is that called? This is not a lookup table. This is a switching table where for each level, for the first level, for the second level, for the 0 level, which switches needs to be turned on among the 6 switches. If you have 6 number of switches, what are the switches you will turn on? That I have represented here. And same way, we'll not go into this. These are the simulation results. You can see the output voltage and the current. Like I have shown you, if I change the load at this point, only the current is changing from resistive load to somewhat sinusoidal type of waveform because of the filtering ability of the inductor. Whereas output voltage is never disturbed. And the capacitor voltage, if you observe it here, it is maintained as desired. Whatever the desired voltage, accordingly capacitor voltages are maintained here. So this part I will not go into. This is one of the design we have done it here. This is one of the design where you can see this is the TLP250 what I was talking about, driver, and these are the switches what we have used here. And this circuit what you see is actually used as an SMPS used here just to supply the isolated supply for this driver or for this TLP250. You need a supply. Otherwise, it cannot actually amplify your pulse from 5 volt to let's say 15 volt you want to amplify. The 15 volt actually is produced from here. And 5 volt pulse will come from the controller. So both it will take into account, then it will generate a final pulse for the switches. Is it clear? This way we have designed, again we have designed with a DSP board, the same high-end type of design we have done it for using a non-linear load, diode-based type of rectifier load. And these are the switched capacitor what you see here. So these outputs are not required. In the real time, if you see here, we have observed the output for fundamental frequency control and for high switching frequency control also. So before I close this, I will just show you some simulation model. Again, there is a less time, so what I will do, I will not go into the circuit design part. But if you can see here, I have used a single DC source, and that I have mentioned at 100 volt. These are all the IGBT switches. You can utilize actually IGBT or MOSFET, any type of switch. And in this circuit, just to show you a feel of a 7-level circuit, what I was showing you from the starting itself, 7-level. For a 7-level cascaded H-bridge, you need actually 12 switch. Here, I have used only 9 number of switches using 2 capacitors. And you might be wondering how the capacitor values are chosen. See, the capacitor value selection is the most important part. So, you must choose the capacitance value, remember, by one factor that is called as the level and how it is discharging time. So you must consider the discharging time of the capacitor. Why? Because the capacitor current, what will flow through the capacitor, that depends on the ripple voltage with respect to time. So the capacitor current needs to be minimized every time. And to design, if you do not design the capacitor appropriately, the capacitor current will be very, very high. Right? So that's why you need to choose the capacitor appropriately, looking at the discharging time of the capacitor. Look at the discharging time. Why I am telling you discharging time? Because if you see this capacitor, let us say this capacitor, is charging here and it is discharging continuously up to this level. The discharging time is quite large. So looking at the discharging time, you can actually decide the value of the capacitance. So by that calculation, why I have given a value of, let us say, 33 microfarad, 3300. Right? It means 3.3 millifarad capacitor, both same value. So when this switch S1, S2 is conducting, my output voltage will be definitely V. But when these capacitors are adding into it, then my output voltage will be 3 times the input voltage. It means with just 100 volt, I will be getting actually 300 volt. So to give the generator switching pulses, what I have done here, I have shown you just now the programming. This is a different type of programming. I am showing you a simplified version. This is for each level of the positive level and negative level, right? Don't worry about how this 0101 are written. Once you design any circuit, you will be actually able to write the switching table easily. Switching table, how you will write? It must be clear in your mind how to generate different levels. Once that is clear, you will be able to design a switching table. Once switching table is done, now you can integrate any type of harmonic elimination control or any type of PWM control. Here, from the control scheme, I have taken just 3 angles. Why I have taken 3 angles? Because I want to generate only 7 level output. Now you can similarly create a logic table or a lookup table where you can store all your switching angles and you can process it actually. So by that, if I now run with a different type of load, let us say, okay, this is up to from 0.1, within 0.1 second, R load is connected or resistive load is connected for some time. And after that, I'm switching on to RL load, inductive type load. So if you observe this output here, the blue color graph shows the current. Okay, the voltage is not disturbed when changing load from R to RL. Capacitor voltages are maintained as desired. Both the capacitor I told you will be maintained at 100 volt. You can observe it. The charging discharging is very much clear here, right? Capacitor is getting charged and discharged. If you see the voltage ripple, you will realize it is approximately 5%. 5% of the output voltage. Same way, the other capacitor is also getting to charge to approximately 100 volt. Here you can see the peak voltage is approximately 100 volt. That is the reason. See this graph output voltage. I am getting red color one. I am getting 300 volt output with one DC source, two capacitors. Right? I am getting 300 volt, and the load current I am getting same as the output voltage pattern for R load. For RL load, I am getting nearly sinusoidal, I can say. So this way, actually, you can start doing the test. There are, I know, many doubts might be there. Why, how to still simulate it? So my suggestion is to start doing the simulation from a basic 3-level inverter cost or basic 5-level inverter cost. Basic 5-level inverter, what I mean to say is this type of structure what I've shown you. Here, you can start designing this type of 5-level structure cost, where there are only 6 switches, right? So with this, if you do this test, I think you will be more clear. And then anytime if you are getting any doubt, I'll be there to help you. You can refer these papers. Some of the papers are there on harmonic elimination control. If you want to get work on that. If you do not want to work on only multi-level inverter design, you can work on harmonic elimination control, taking into account just the cascade edge bridge also, or just the conventional inverter, take into account and work on different types of control schemes. If you want to design different types of multi-level inverter, then you can focus on the recent type of inverter design which are based on switched capacitors actually. Extendable switched capacitor or switched capacitor. These are different type of design which is coming into play very recently. So I hope there are many concepts. What I wanted to share with you is clear, but any doubts you may contact my email ID, or if you have some time now, 5 minutes maybe, you can get quickly some questions. Sir, are you there? Arnab sir?
Hello, sir. I'm here.
Yeah, am I audible, sir?
Yes, you're audible. Thank you, sir, for the session. So I'm requesting the participants any queries from your end, so please let us know. Okay. I hope there is no doubt, sir. From the actually your session was very good. Means step by step how we are discussing. So that is really good. I hope a lot of information they have. I mean, they are able to learn from you. Okay, sir. So I have also learned. I have also attended most of your session, but I am going to the department. I am also the meeting. So that's why some of the portion I have missed also. But the overall session is very good. So actually I'm thanking you for your valuable time that you have given us for your uh,
It's
session.
my pleasure, sir.
So
Be around
in
all
near future, yes, near future again we are requesting you for some deliberations of your lecture.
Sure,
So
sir.
thank you, sir.
Any doubts
Thank
from
you.
the participants?
Yes, sir.
Any doubt you can contact me on my email ID.
Sure, sir. I'll share your contact number with them. So if any doubts, so definitely they will mail you. Mail
Sure,
ID
sure.
I'll share it.
Sure.
Okay, sir. Thank you, sir.
Thank you again once again, sir, giving me this opportunity.